Okay, today we're going to be looking at combining the transformations that we've been looking at. So let's look at what transformations we've already got. So if we were transforming for graph y equals f of x, we've got these vertical transformations, so parallel to the y-axis, and these horizontal translations parallel to the x-axis. Now it's really important that we differentiate what we mean, if it's going to be a vertical transformation or a horizontal transformation. So here we have the vertical transformation where it's a translation, and it'd be 0, the x-axis, the x-coordinate remains unchanged, but we change the y-coordinate, and that's f of x plus a. Then we've got a reflection in the x-axis where y of x becomes negative, and then we have a vertical stretch of factor a when we multiply the graph by factor a. Then we've got the horizontal translations. When y equals f of x plus a is a translation where which is described by the vector minus a, 0. And then we've got the reflection in the y-axis where y becomes f of minus x, and the horizontal stretch is y equals f of ax with a stretch factor of 1 over a. So, and the reason that we differentiate these is because when we combine transformations, oops, again, we need to be aware of the order. So just like in arithmetic, if you're adding two things together, the order doesn't matter. Likewise, if you're multiplying two things, the order doesn't matter. But if we were to subtract two numbers or divide two numbers, the order which we have those numbers matters. And that's the same with transformations. Sometimes the order doesn't matter, and other times the order does matter. And it's a really worthwhile exercise to take some time to look at different ways of combining transformations and getting a real handle on through trying them and playing with them, when it matters and when it doesn't. So what we will find is when two vertical, I'm not spelling properly tonight, vertical transformations or two horizontal are combined, the order does not wait a minute, sorry, that's the wrong one. The order in which they are applied may affect the outcome. Sometimes it won't, but if you're doing two vertical transformations, the order in which you do those transformations may affect the outcome. Likewise, if you were to do two horizontal transformations, the order may affect the outcome. When one horizontal and one vertical transformation are combined, the order in which they are applied does not affect the outcome. So it's really important that you remember these two little statements. They're really important. And when you combine it with the list of transformations that we had on the previous slide, that's all of that together is really important that you memorise and you know, that you feel really comfortable with working with these ideas. So we're going to look at a couple of examples so that we can just explore these things more fully. And I don't have squared paper here, so the pictures are going to look not very good. But I'll try and explain it as we go along. So the diagram shows y equals f of x now. Let's try and draw this. Oh dear me, that was terrible. So x and we've got y, and so this bit's straight, and it's meant to be at 1, okay? And then it goes down like here, and this is 1, and then it goes up quite sharply, and that's 2, and then along, and again it's straight, and that's 3. So this is y of f of x, and we want to sketch y equals 2 of f of x minus 3. So the combination of two vertical transformations so they follow the normal order of operations. So that would mean, so with the order of operations, because the order matters with vertical transformations, the normal order of operations would be you multiply first and then you divide, or you add or subtract. So we will sketch, so first we're going to sketch y equals f of x with the stretch factor 2. So I'm going to redraw it. So where that was going through 1, that's now going to move up to 2. And this bit here was at minus 2, minus 1, sorry. So timesing that by 2 is going to be minus 2 down here. But the x coordinate stays the same. And then this is going to shoot up to 6, because that was at 3 before, and then it goes straight on. So that equals y equals 2 of f of x. Now we will sketch y equals 2 of f of x, minus 3. So we take 2 of f of x and translate by vector 0 minus 3. So we're taking what we've done the stretch, and now we're going to do the translation. So all the y coordinates are going to change by 3, minus 3. So here we had this was at 2, so this is going to come down. This bit here is going to come down to minus 1. This bit here was at minus 2. That's going to come down to minus 5. And then here is going to go back up to 3. And that is the sketch of the full translation. Now obviously when you're doing it, you do it on graph paper, so it shows much more accurately than my little sketches here. So now we're going to look at the diagram of y equals x squared, and its image y equals g of x after a combination of transformations. Okay, so I'm going to draw y first. Okay, there we go. We'll change the colour of that we're drawing it in, so that we can draw the translation and you can see where it's at. So this will be this is 0 and this is 2, and it comes up to the height 4 in both cases as its height, and it's at 4 at 1 here and minus 2 here. So we want to find so what we want to find is two different ways of describing the combination of transformations. So let's think about it. What transformations do we have? Well, we've got a translation and we've got a stretch. There's no reflection. So we can do the translation first, followed by the stretch, or the stretch first, followed by the translation. Now, this is in the horizontal. So I'm going to just write beside us the rules for the translation and the sketch. I'll just write them down here just so we've got them. So y equals f of x plus a, and it's got a translation vector of minus a, 0. And for the stretch, we have y equals f of a x with a stretch factor of of 1 over a. Now, let us think about the translation first. So it's moving along the x-axis in this direction. Now let's think about it. If we had, I'm going to put a completely different colour on. I'm going to put on orange, will show up. So if we moved it by 2, it would it would come here. But let's think about this coordinate here. Move that by 2, it would come to 0. So we'd have something like, that's terrible. Like that. Then, let's think of if we did a stretch with this and did it by half. So that's at minus 2, and we've moved it by 2. So 0's here. Then if we did a stretch by a half, so the x coordinate is now going to go by a half. 2 would come to 1. That's not going to, you're going to end up with, and then it's not going to look the same. That bit the thing that's here, the minimum is going to end up on the 1. So it can't be a translation where it's moved by 2. So let's get rid of the orange. Let's think of a translation by 3. So the minimum is going to move to the 3. And then when we stretch the 3, we're going to consider that by just a half. A is going to be 2, so it would be a half. 3 divided by 2 is going to be 1.5. The minimum of our new image, g of x, is in the wrong place. So let's think of a translation where we move it by 4. So we move it to 4. And I'm going to draw this as a dotted line. So minus 2 is going to go to plus 2. It's going to go up to here. Now, if we now do a stretch where a is 2, it's going to be, that's going to move to here, and our coordinate that is up here, which is now on 2, the half of 2 is going to be 1, so that's going to come here. This coordinate, which is 6, will move to here, because that's 3 here, and you see this is what we have. So we have a translation where of a being 4, so we move the minimum into 4, then a stretch factor of a half. So that's one way of combining them. Let's think of doing the stretch first. So if I'm going to just draw it again, it's far too big. And I'm going to put the g of x again in a different colour. There we go. So let's put some numbers on this. So that's there. That's at 2. Again, this is minus 2. The top's 4. And that's maybe 3. So let's think. So now we're going to do the stretch first, plus the translation. So we're going to try a stretch factor again of a half. When you're doing these kind of trial and error things, go with what's easiest first and what kind of makes sense. So half makes sense. So if we were to take this and translate it, so there's half of 0, 0, so the minimum stays there. 2 goes to minus 1. So I'm going to do a dotted line. And then 3 goes to 1.5. It's going to kind of come up here. Like that. So this looks like it could work. 2. Oh, this bit here. Sorry. So this bit here is at 2, and so that is going to come up here at 1. That's meant to be up here. So this looks promising. So let's look at if we have a stretch of half. Then if we move everything by 2, the minimum is going to go to here. This minus 1 will go to plus 1, which is here, and so we end up having the right translation. So we've got a translation of 2, 0. Now, we want to use the combinations to find the equation of g of x. So, let's look at what we've got here. So for so y equals x squared. Translation for 0 means y equals f of x minus 4. So where we have x, we're going to put x minus 4. So y is going to become x minus 4 squared. For the stretch, of a half, y becomes f of 2x. So where we have x, we're going to put 2x. So therefore g of x is going to become 2x minus 4 squared. Now if you were to do the same process but use the other combination, you would find the same thing. Because although the combinations, the way in which you combine transformations varies, and you have the transformations themselves are different. Once you combine them and find the equation of the line, the image g of x is the same, even though the path you get there is different. So that's a really good exercise if you try this and use the different combination. So I hope that helps.